Alright, thanks for watching, and today I would like to tell you about a really cool formula for fractional derivatives, which is kind of like a binomial formula for half derivatives, if you like. And it's what's called the Grunwald-Letnikov formula. And Grunwald means like green forest in German, so it's a nice name. And let me give you some motivation. Of course, all the motivation for fractional derivatives come from regular derivatives. So let me talk a bit about motivation. So what is the definition of the derivative? F prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. Hopefully we can agree on. And in particular, if you remember, there's a similar limit definition for the second derivative, which is as follows: f double prime of x, that's limit h goes to 0 of f. So it's f prime of f prime of x. So it's limit as h goes to 0 of f prime of all that, x plus h minus f prime of x over h. And which really becomes the limit as h goes to 0 of the limit as h hat bar, if you want, goes to 0 of f of x plus h bar minus f of x plus h over h bar, and then minus, if you want, limit, I don't know, h bar goes to 0. H walks into a bar. F of x plus h bar minus f of x over h bar over, this is barbaric, over h. Okay, and you know, this is just for motivation, so assume everything exists, everything is smooth, then you can kind of do some diagonal argument and just say, you know, h equals h bar equals h bar bar. So what you're left with is then just the limit h goes to 0 of really, you know, f of x plus h, so f of x plus 2h minus f of x plus h, and then minus, minus f of x plus h, and then minus, which becomes plus f of x over h, so over h squared, and you can simplify this as limit h goes to 0 of 1 over h squared f of x plus 2h minus 2 f of x plus h plus f of x. And then there's a beautiful Leibniz formula, yes, the Leibniz, that basically says you can rewrite this in terms of binomial coefficients, and that is also true for higher derivatives. So if you want, that is really the limit as h goes to 0 of 1 over h squared of, if you want, the sum from m from 0 to 2 of minus 1 to the m, to choose m of f of x plus 2 minus m h. Why does that make sense? Because if m is 0, we get f of x plus 2h. This becomes plus, and 2 choose 0, it's 1. Okay. And if m is 1, we get a minus, which we have here. 2 choose 1 is 2, and then f of x plus 1h, which is here. And lastly, if m is 2, we get a plus. So what this says is just alternate sign. 2 choose 2 is 1, and then we get f of x plus 0, which is f of x. And just a little convention, so it turns out if m is bigger than 2, we just say 2 choose m is 0. If m is strictly bigger than 2. So you can really write this as an infinite series, and you'll see why this is useful. So this is really the same thing as the sum from m from 0 to infinity of this because all the other terms are 0 then by definition. And this is, if you want, the definition of the second derivative, f double prime of x, which you can write as a limit of a sum of a bunch of binomial things. And it turns out, and people ask me, is there a limit definition for the fractional derivative? Yes, there is. Literally, you take this formula and you replace 2 by alpha. So, the fractional derivative of f is then the limit as h goes to 0 of 1 over h to the alpha of sum from m from 0 to infinity. This all stays the same. The only change is this becomes alpha choose m, which I'll define in a second what this is. F of x plus alpha minus m, h. And alpha choose m, exactly the same definition as for integers. You just start at alpha and then multiply it by smaller and smaller numbers, but you stop precisely at m minus 1. And you divide by m factorial. So you might think of it as n factorial over n minus k factorial times k factorial, but this is really just saying you start with n and then you just multiply smaller and smaller values until you get k minus 1. Okay, so this is what's called the Grunwald-Letnikov formula, which gives you a definition of the fractional derivative for at least positive ones. It gives you a definition of a fractional derivative in terms of a limit. So in particular, today let's apply to half derivatives. The glass is half full today. And so we get that the half derivative is then the following formula for us today. d1 half of f is then just equal to the limit as h goes to 0 of 1 over square root of h times the sum from m from 0 to infinity of minus 1 to the m, 1 half choose m of f of x plus 1 half minus m h. So it's kind of interesting. Yes, what does the half derivative say? It says you're just taking this limit and then, just like derivatives are kind of linear, half derivatives are kind of like square roots, and you're summing it over this alternating sum of bunch of numbers, and you're sampling f at different points. Just like in the derivative, you're sampling f at 2 points, x and x plus h. And so I was thinking, well, maybe I can use this to calculate the half derivative of x. But even in this point, I was a bit confused because you have to sum up all those bunch of things. But so I'm not going to do this, but instead I will show you this is consistent with the definition of the half derivative. Namely, what I want to show today is that the half derivative of the half derivative with this definition indeed gives you f prime. And it's a very beautiful formula. Because suppose let g be the half derivative of f. And let's calculate the half derivative of g. Ideally, we want to show this equals to f prime. By definition, the half derivative of g is the limit as h goes to 0 of 1 over square root of h, sum from m from 0 to infinity of minus 1 to the m, 1 half choose m, of g of x plus 1 half minus m h. Okay. And now g is its own definition. It's just this whole huge limit. So what you do, you then just plug it in. So this is, I know, a lot of work to do, but we can do this. Okay, this then becomes the limit. Still, the beginning is the same. Limit h goes to 0 of 1 over square root of h, sum from m from 0 to infinity of minus 1 to the m, 1/2 choose m. And then instead of g, you now replace it with the definition, except, and here's a complicated thing, I think you replace x by this whole thing. So it becomes times the limit as, let's say, h bar goes to 0 of 1 over square root of h bar, sum over something different, k from 0 to infinity, minus 1 to the k, 1/2 choose k, and f. Again, the beginning is the thing in g, so 1/2 minus m times h plus 1/2 minus k times h bar. Okay. All right, and then, well, in order not to confuse ourselves and assuming that everything converges nicely, and assuming this line will work at some point, let's assume h equals to h bar. So using, if you want, some kind of diagonal argument, and you get limit h goes to 0. Because h is h bar, you have 1 over square root of h times 1 over square root of h, which becomes 1 over h, just like what we want for the derivative. Then we have sum m equals 0 to infinity of minus 1 to the m, 1/2 choose m, and then sum k from 0 to infinity, minus 1 to the k, 1/2 choose k, and then f of x plus 1/2 h plus 1/2 h, which is x plus h, and then minus m plus k h. Sorry about that. And this, if we want, pull that inside and we get a double sum. So it's limit h goes to 0, 1 over h, sum m from 0 to infinity, sum k from 0 to infinity of minus 1/2 to the m times minus 1/2 to the k. It's minus 1/2 to the k. So m plus k, and then 1/2 choose m, 1/2 choose k of f of x plus h minus k h. I know it's horrible because we have a double sum, but look, this looks pretty promising because remember, we want to show this equals to f prime. We already have this 1 over h, and this, we already have this x plus h minus something h. So we're kind of on the right track here. Now, next thing we want to do, notice, we have a m plus k here, and we have a m plus k here. So kind of change variables. So let this be L, and let this be L. And what are we summing on? You notice this is kind of like a double integral, but discrete-wise. So this is really the sum, if you want, over all k and over all m. Something like that, k and m. And what we want to do, we want to sum over the sum, literally, of m plus k. So this is m plus k equals 0, m plus k equals 1, m plus k equals 2. So really, to sum over all the dots, it's the same as summing from k from 0 to infinity and summing over all those diagonal lines, which is really L from 0 to infinity. So what this becomes is then the following limit, maybe almost done, kind of, sort of, I don't know. There's just a little manipulation left, and then this one's justification. So it's then the limit as h goes to 0 of 1 over h. Then what I said, this becomes, we sum over k from 0 to infinity. Then we sum over L from 0 to infinity, and L is m plus k, so minus 1 to the L, 1/2 choose m, and then, sorry, 1/2 choose k. So 1/2 choose something times 1/2 choose k. Now this before was m, but look, m plus k is L, and now we want to write this in terms of L and k, so m is L minus k. L minus k, like, which hopefully you will do to my video, so I like it. And f of x plus h minus LH. Which is good, because I think that's almost part of the definition. So we ideally want no, actually precisely, because this becomes f of x plus 1 minus LH. And remember, for the half derivative, we had 1/2 minus m, and for the fractional derivative, we want x plus alpha minus mh, which for alpha equals 1, so for the ordinary derivative, we want an x plus 1 minus mh. And m is just a dummy variable, so we have achieved this part, f of x plus 1 minus LH. Now, and we also have this minus 1 to the L, we also have this. So a bunch of parts were good. The only things we still need to fix, this double sum, we want it to be a single sum, and somehow this thing, we kind of want to turn it to like 1 choose L or something. So, what can we do? So we have this double sum, just like usual. Let's switch the double sums, because this only depends on L, this also only depends on L. So let's switch that. So we get limit h goes to 0, 1 over h, sum from L from 0 to infinity, and then sum from k from 0 to infinity of this whole chunk, minus 1 to the L, 1/2 choose L minus L, choose blah blah, 1/2 to the k, and then f of x plus 1 minus LH. And that's good, because there are a bunch of terms that we can just pull out. We can pull out this thing, minus 1 to the L, and we can pull out the f term. So what we're left with is the limit as h goes to 0 of 1 over h, sum L from 0 to infinity of minus 1 to the L, f of x plus 1 minus LH, and then sum from k from 0 to infinity of 1/2 times L minus k times 1/2 choose k. And look, we are almost done. In order to show this is the derivative, all we need to show that somehow this equals to 1 choose L. Because I believe, again, that's the definition of the derivative in terms of our Leibniz formula. And then let's show this. So basically, the only thing left is as follows. So claim all we need to show is that the sum from k from 0 to infinity of 1/2 choose k and 1/2 choose L minus k equals to, again, we want to show that it's 1 choose L, but what is 1 choose L? It's simply 1 if L is 0 or 1, and 0 everywhere else. It's kind of like the trivial Pascal triangle. So 1 if L is 0 or 1, L equals 0 or 1, because I think we do have, 1 choose 0 is, 1 factorial over 1 minus 1 factorial over 0 factorial, and also 0 if L is greater or equal to 2. So as I said, once we have that, we are done, because that would be 1 choose L. And then what we would get is the half derivative of the half derivative of f would be this formula, which is precisely the definition of f prime of x. Because, you see, if L is greater than 2, then we would just get, this is 0, so this is really the sum from 0 to 1, and it would just become a limit h goes to 0 of, let's see, if L is 0, it would be f of x plus h minus f of x over h, which is then precisely f prime of x. So that's all we need to show, and this one is a very cute proof as well. So why is that true? Well, notice square root of 1 plus x times square root of 1 plus x equals 1 plus x. And you're like, what? Like, what does it have to do with anything? Well, if you remember your Taylor series, or your fractional Taylor series, unfortunately I forgot that sweater, a very nice sweater and a very nice shirt. You can expand this in terms of Taylor series. So this is really the sum from m from 0 to infinity of 1/2 choose m times x to the m. And this is the sum, let's say from k from 0 to infinity, of 1/2 choose k x to the k. And we know that this is 1 plus x. Then just expand everything out. So if you want, this is the sum from m from 0 to infinity, sum from k from 0 to infinity of 1/2 choose m x to the m times 1/2 choose k x to the k. And that equals to 1 plus x. Then put everything together, so this becomes, if you want, switching the sum, so that is the sum from k from 0 to infinity, sum from m from 0 to infinity of 1/2 choose m, 1/2 choose k, x to the m plus k equals this, equals 1 plus x. But just as before, if you let L be m plus k, the left-hand side then just becomes the sum from k from 0 to infinity, the sum from L from 0 to infinity of 1/2 choose k, 1/2 of L minus k, x to the L, equals 1 plus x. But notice you can write this, if you want, as also a power series, so that's the sum from L from 0 to infinity of basically, let's say some number, an, so al, x to the l. And what is al? It's precisely a0 is 1, a1 is 1, and al is 0 for l greater or equal to 0. So a greater or equal to 2. So a0 is 1, a1 is 1, and al is 0 for L greater or equal to 2. And then all you have to do is, I guess, switch that sum again. So I don't know why I switched it, but this becomes the sum from L from 0 to infinity, sum from K from 0 to infinity. And then literally just compare the two. So this coefficient, this huge coefficient, which is the left-hand side, equals to AL, and in particular, what do we get? If L is 0, this coefficient is A0, which is 1. If L is 1, this coefficient, which is A1, is 1. And if L is greater or equal to 2, this coefficient, which is what we want, is AL is just 0. So we have this beautiful little power series trick to show this. And yeah, And basically, that is, we're done. We have indeed shown that with this definition of the half derivative of the half derivative is the ordinary derivative. So if somehow maybe you can show that half derivatives are unique, even though I don't think so, all the coefficients, all the definitions then coincide. Alright, I hope you like this little fractional extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.